All right, so at this point in time, we talked about uniform circular motion a little bit. We've realized that we can calculate speed from 2 pi r over the period of motion. We also talked about how that the acceleration that an object would experience when traveling a uniform circle would be equal to v squared over radius. And then we probably had a few problems where we dealt with finding the net force acting on an object by taking MAC, that centripetal acceleration, and that being equal to F net, which a lot of times people refer to as F centripetal. However, try to avoid that because then we don't get confused with like somehow that's some sort of force that actually is not just a result of all the forces. So from this standpoint, then we can look at several different physical situations and the forces involved, so we can try to look at determining when those forces and what those forces might be. A couple of primary examples are we have a mass on a string swinging in a vertical circle. Right at the top of that mass, the top of that circle, the forces acting on that object are obviously the weight mg of the object, and in this case, the tension in the string. And it's that tension in the string that causes the object and the weight, both of those things, pulling, accelerating the mass when it's at the top of the circle toward the center. So if we looked at that case and looked at the sum of the forces, the sum of forces should be equal to MAC, and those forces should be tension plus mg. And then obviously we can resolve that situation to find out how much tension the object would have if it were traveling at a particular speed. Remember that most of the time we're going to make that v squared over r substitution for a centripetal. So in this case, the tension in the string would be equal to MAC minus mg. A lot of times we try to think about, or a question that's commonly asked is, what minimum speed would the object have to remain in that circular path? And to look at that situation, the sum of forces equal mv squared over r, which is ma, and they should be equal to mg plus tension. If I want the minimum speed, I can just set the tension equal to 0. And when that happens, then the only thing that's keeping the object accelerating toward the center would be its weight if there were no tension. And I look there, and then I get mv squared over r equals mg if tension equals 0. And that minimum speed then should become the square root of gr once my masses cancel and I resolve that. And that's a pretty common application of the situation with the vertical circle at the top. Another example where we would see something similar to this would be, for example, the roller coaster loop, where we're inside. We have our roller coaster car at the top of the loop. Forces acting on it here are obviously mg of the cart or the passengers, as well as the normal force from the track onto the cart, or the seat of the cart onto the person who's sitting in the cart. And we would have the same situation. Sum of forces equal mv squared over r, F equals ma, Newton's second law, and those forces should be mg plus normal because they're both acting to pull that cart and accelerate it toward the center of the circle for that brief moment when it's actually at the top of the loop. Minimum speed here would be a similar situation. So to find V min, set the normal force equal to 0, and then it's just going to be the weight of the cart pulling it around that loop, which would be the minimum speed. Obviously, that gives people who design roller coasters a chance to figure out, hey, it's got to go at least this fast. So now if we design it so it's going 2 or 3 times that fast, the chances of having an accident where there's not enough force involved or people are falling out of the cart become minimized. So those two examples from applications of the real world where we look at trying to find those things when we have things at the top of that circle. The other obvious case where we would look would be where we have something occurring at the bottom of a circle, like the mass on a string. And there are several different applications that are similar to that situation. We have our object at the bottom of the circle. And there's our radius. So the object at the bottom of that vertical circle, the circle's not very solid. Here, free body diagram, we have the weight of the object down and tension pulling up. Our direction of our acceleration here is up, so when we look at the sum of forces should be equal to MAC. The direction of the acceleration is up, so it should be tension minus weight, or mg, so that mv squared over r plus mg should equal tension in this case, realizing that the tension that's in the string not only has to support the weight of the object that goes around, but it also has to provide enough extra force to cause that object to continue to accelerate. An example here we would look at, oftentimes, or a question we might see would be, if the tension will break if it exceeds 20 newtons, find the maximum possible speed that we can swing the object, or the maximum tangential speed that it can have, and still not break the string. That's a pretty common question with those masses on string situations. Other situations that we see here that are analogous to this or have a similar situation, people riding on a Ferris wheel. At the top of the Ferris wheel, the forces are mg up, Another example, cars going through a dip or down at the bottom of a hill. Here we have normal force up and mg down. The radius of curvature for our turn is there. So we have the same situation. Sum of forces equal mv squared over r, and they should be equal to normal minus mg. At the top of a circle, or the top of a hill, we still have normal up and mg down. However, in this case, our acceleration is downward. So if we're at the top of the hill, or at the top of a Ferris wheel, in either one of those cases, the sum of forces equals mv squared over r. And in this case, because my acceleration is down, I should have mg minus normal. So that normal should be equal to mg minus mv squared over r. Situations where this comes into play, what's the normal force going to be at the top of the Ferris wheel, which is one of those reasons why people ride it, because when you come over the top, you feel as if you're becoming weightless. A car at the top, or a roller coaster car at the top of the hill, how fast can it go over the hill before you become weightless would be an example where you would just set normal force equal to 0 again. With the roller coasters, what would the normal force be if you travel at a certain speed? Oftentimes we ask the normal force, we should recall, is oftentimes referred to as that apparent weight. But having different situations there that we can look at and analyze the forces, realizing that we really need to find out direction of acceleration and set up those Newton's law statement so that the forces are represented properly in terms of their relationship to each other. Obviously, the forces in the direction of acceleration minus the other forces should give us that proper setup. So that should give you a good handle on the different physical situations that we find oftentimes when we talk about uniform circular motion. And there should be a list of problems online as well that you can, on the CFAF physics1.weebly.com, that you can go on and give them a try tonight on your own, and then we will discuss them tomorrow in class.